Okay, there are two main things we're going to talk about today. Electric flux and Gauss's law. These are two independent quantities, or two independent concepts, but together they allow us to calculate electric fields from some situations that we haven't looked at so far. Remember, what we talked about so far are electric fields produced by point charges or by collections of point charges, or by a surface where we integrate Coulomb's law over the entire surface or object. With Gauss's law, we can solve for electric fields in certain cases that are very complicated, but if we have a particular symmetry, then we can use Gauss's law to calculate the electric field pretty quickly. So first of all, let's talk about electric flux. This is a very confusing topic, but it's very important for you to learn it because you're going to be using the idea of flux in a vector field, not only in electricity and magnetism, but if you ever take a course in heat transfer or a course in fluids, you're going to have to learn about the rate at which fluids flow or the rate at which heat flows, and it uses exactly the same mathematics that we use to describe electric flux. What we're going to look at is sort of the simplest possible cases of flow, and when you look at it later on, you will have it with all of the calculus of vectors that you need to handle it. So let's define what an electric flux is. Let's suppose we have an electric field, E, that's going through space, and we define some surface, which I'll draw just here as a circle, so that the electric field lines go through that surface. And the surface has an area A. So if we have a whole bunch of field lines going through the surface, you can think of it like it was the flow of a lot of water through the outside, through the end of a pipe. And so we would measure the flow of water, for instance, in the number of gallons per minute of water that go through the end of that surface. Well, in this case, we're going to measure the flux, which is the electric field times the area, in a sense. But we have to be very careful about how we define the area. And notice that the amount of electric field that goes through an area depends upon the relative orientation of the surface and the electric field. So for instance, suppose I have an area that looks like this. It's a square or a rectangular sheet of paper, and I have an electric field going this way, horizontally. Well, in this case, the electric field lines are all going perpendicular to the surface, and so I would have a lot of coverage of the electric field going through that surface. But if I take the same surface area and turn it like this, and then have the electric field lines going in this direction, going that way, then all the electric field lines are going to go either above or below the surface, but not actually through the surface. So in this case, the electric flux is going to be 0, but if I turn it this way, the electric flux is going to be as large as it can be because the surface is actually perpendicular to the electric field lines. So let's figure out how to take into account the area of the surface, the strength of the field lines, and this orientation factor. The way we do this is, first of all, we have to define what the surface looks like, and we're going to define it in terms of a vector. So let's suppose I have a surface. I'll make it a rectangular surface like our page. It has an area A, and we have to figure out some way to denote how this surface is oriented in space. And the way we do that is we define a vector that's perpendicular to the surface of the that we're looking at, and we'll call, and so this vector is perpendicular to this surface. It would be like taking this this marker and putting it perpendicular to the sheet of paper. We call that vector A, and it's also called a normal vector because it's perpendicular to the surface that we're interested in. The absolute value of A, the magnitude of A, is given by the area of the surface. Okay? So for instance, if I were going to take this sheet of paper and define the normal vector for this, the normal vector would be going off in this direction, and the value of the normal vector would be the area of this sheet of paper, which is 9 by 11 inches, so it would be 99 inches squared in that direction. Okay. All right, so you define an area by a vector. That's a little unusual, but that's the way it's done. And if I turn the orientation of the surface, the vector is going to change its direction, but its magnitude will not change because the magnitude is just the area of the surface. All right, well, if I put an electric flux or an electric field through this surface, suppose the electric field is coming along this way. All right, the field lines will go through this surface, but it depends upon how the surface is oriented, and we're going to define the electric flux through this surface in the following way. First of all, we have a symbol for the electric flux. The electric is defined by a symbol phi, and in this simple case, the electric flux is given by E dot producted with the vector A. Okay. Now, if you remember, this dot product always produces a scalar. It's going to have units of newtons per coulomb times meters squared. Electric field is newtons per coulomb. The area is meters squared. This, like I said, this is a scalar, so it has no direction. But the value of the scalar depends upon the relative orientation of E and A. And if I may, let me erase this. So phi is equal to E dot A. That's equal to the magnitude of the E field times the magnitude of the vector, which is just the area, times the cosine of the angle between them, where that's the angle between E and A. Okay? So if you look at this, if the electric field is parallel to the A vector, then we have the maximum value of the flux. And if the electric field is perpendicular to the A vector, we have the cosine of 90 degrees. That's 0, and we would have 0 flux. So let's see, if I have my surface this way, I hold it this way, and I have electric field lines going away from me towards that side, then in this case A is pointed that way, E is pointed that way, A and E have an angle of 0 degrees between them, and we have the maximum amount of electric flux. If I turn the surface by 90 degrees, then the A vector is pointing upward, the electric field is going that way, and so I have a cosine of 90 degrees, and there's no electric flux going through this surface. Okay. So that works. This is exact if I have a flat surface, if I know the area, and the electric field is continuous, or excuse me, is constant in magnitude and direction over that area. Okay? All right. Let's take an